It is very important topic. You can mark it as important. So either any one derivation will come for 10 marks. This is a practical parallel resonant circuit. Ideal means ideal components R L C are connected in parallel. But in the practical parallel resonant circuit, there is no separate R here. So only L and C will be there. In the L and C, first circuit is inductor is having internal resistance R, and another practical circuit, capacitance is also having internal resistance R. So in the practical parallel resonance circuit, no separate resistance will be there parallel. Only LC will be there. Out of LC, inductor is having internal resistance R. That is the first parallel practical resonance circuit. In the second one, in the capacitor branch also, one more resistance will be there. So let us do first one, practical parallel resonance circuit, where only inductance is having internal resistance R. It is connected across voltage E with variable frequency F. Okay. Now impedance of the given circuit, please note down impedance of the coil. That means this, there are two branches, inductor and capacitance. The impedance of the coil is given by these two are in series. Okay, these two are in series, so R plus j omega L. So derivation is very important. You follow the steps. Two branches are there. For two branches you find individual branches impedance of this branch is R plus j omega L. Okay, and you take reciprocal of that, because in parallel circuit you have to consider admittance. Okay, so admittance of the coil is YL is equal to reciprocal of impedance of coil, that is 1 by ZL. So we have ZL is equal to R plus j omega L. So 1 by j L is equal to 1 by R plus j omega L. Similarly, for inductance branch, for this inductance branch we calculated admittance of the coil. Similarly, you have to find out admittance of the capacitance. Admittance of the capacitance is given by, so before that we have to rationalize, you have to separate the real part and imaginary part. We have YL is equal to 1 by j omega L. So in the denominator j is there. So this you have to rationalize and you have to separate real part and imaginary part. So for that you have to multiply with in the denominator we have R plus j, in the denominator we have R plus j is there. So that's why you have to multiply with minus. So if once you rationalize, YL is equal to 1 plus j R plus j omega L multiply with R minus j omega L R minus j omega L. Again, if you cancel it, you'll get 1 only. This part is actually 1 only. R minus j omega L R minus j omega L. So this we are doing rationalizing to get separate real part and imaginary part. So in the numerator you'll get R minus j omega L. If you multiply 1 into R minus j omega L, you'll get this much. And this is a plus b into a minus b. A plus b into a minus b. This is a square minus b square, r square minus j omega L whole square. J omega L whole square, j square omega square L square. But j square is minus 1. J square is minus 1. So we get actually a square minus b square. Because of j squared, we have to write here plus. Because minus of minus 1, j square value is minus 1. So it becomes plus r square plus omega square L square. So in the denominator, j part is removed. Now we can write real part is r by r square plus omega square L square minus imaginary part is minus j into omega L by r square plus omega square L square. That is, we can separate real part and imaginary part. Similarly, we have one more branch, capacitance branch. Impedance of the branch containing capacitor is given by Zc is equal to minus jXc. Because for capacitance you have to write reactance minus. For capacitance you have to write minus jXc, that is the impedance, and x is given by 1 by omega c. X is given by 1 by omega c. And admittance of the branch containing capacitor is given by yc is equal to 1 over reciprocal of impedance. So minus j by omega c. This omega c you have to bring it to numerator. This minus j omega c you have to bring it to numerator. And this minus j if you bring it to numerator, okay, 1 by j is minus j. 1 by minus j is plus j. So here we have 1 minus 1 by minus j becomes plus j. This will go to the numerator. We have yc is equal to j omega c. Now we have to find total admittance of the circuit. We have what we did. We calculated impedance of this coil. Then admittance we have taken. Similarly, we have taken the admittance of this coil. Now total admittance we have to add. So total admittance of the circuit is okay. Then admittance of inductance path, admittance of capacitor path. So in the after rationalizing inductance path, we have this much r minus j omega l divided by r square plus omega square l square, and this you have to separate. Real part is r square plus omega l square, and imaginary part is minus j omega l, same denominator to write, r square plus omega square l square, and here also one more j is there. Here also one more j is, this is because of capacitance path. In the capacitance path, total admittance of this capacitance path is minus j omega c, and here also we have minus j. So here you can take j common. If you take j common, here plus j is there, here minus j is there. So plus j if you take common, first you have to write omega c minus omega l by r square plus omega square l square. And we know that in series resonance or in the parallel resonance circuit, okay, at resonance, for the circuit to be resonance, the impedance of the circuit should purely resistive, or the admittance. There should not be any reactance should be there, or admittance should be there for a resonance condition. So this part should be 0. So if we equate at resonance, if we equate this part is equal to 0, that means omega c should be equal to this much. So and omega replaced by omega r, that indicates that at resonance only. This is possible only. This is equal to this means only at possible at omega at resonance frequency. So omega is replaced by omega rc is equal to omega rl by r square plus omega square l square. Now omega r will get cancelled both sides. This left side, if you bring r square plus omega square l square is equal to, this l is already there, this c you have to bring here. Okay, this you have to bring here, this l you have to bring here, c you have to bring here, this you bring here, this c you bring here. You'll get r square plus omega r square l square is equal to l by c, and omega r square l square is equal to this l by c minus r square. This r square you have to bring it to right side of this equation. And next we have to get expression for omega r. No? So omega r square is equal to l by c minus r square by, you have to divide by l square. This full thing you have to divide by l square. Then you will get, for the first term, l will get cancelled with this l. L by c by l square means l will get cancelled. We left with denominator lc, 1 by lc minus here r square by l square. Here r square by l square. Here also l square will be there. Here also l square will be there. I can write here l by c into l square. This is r square by l square. This square will get cancelled. So we left with 1 by lc minus r square by l square, that is equal to omega r square. So omega r square is this much means omega r is equal to root of 1 by lc minus r square minus r square by l square radians per second. This is radians per second, and frequency is given by 1 over 2 pi, because omega r is 2 pi fr. Omega is 2 pi fr, so fr is equal to 1 over 2 pi of root of 1 by lc minus r square by l square. Suppose if the inductance is not having any internal resistance, if the inductance is not having any internal resistance, if the inductance is not having, that r is equal to 0. If r is equal to 0, what is the reduced expression? If r is equal to 0, this part is 0, and your circuit equation is becomes 1 over 2 pi root of lc. It becomes 1 over 2 pi root of lc. It is same as parallel resonance circuit resonance frequency equation. So this is very important. This will be asked for 10 marks. Procedure is simple. I will repeat once again. Get the impedance of this branch. Get the impedance of this branch. Take the admittance. There is a reciprocal of this, and do the rationalization. For this also, you get the admittance. Next, to add total admittance. Separate real part and imaginary part. At resonance, the circuit behaves as purely resistant admittance, and you have to equate this part to 0. Imaginary part you have to make 0. If we equate, and omega should be replaced by omega r. If we equate, you will get this. Omega r is equal to root of 1 by LC minus r square by L square. This is the required equation. I can easily get 10 marks for this derivation. And two more terms. What is the impedance of parallel resonance circuit? So we have dynamic impedance. At resonance, the admittance of the circuit is purely resistance. Okay, here this part is 0. So this part is 0. So the admittance is purely resistive. This part, this much only. This part is 0. So that is actually called as at resonance. The admittance is purely resistance. So YR is equal to R by R square plus omega R square L square. But R square plus omega square L square is equal to L by C. Here we got R square plus omega R square L square is L by C. This is we got from this. If we equate this is equal to 0, this is equal to this much, means we got R square plus omega square L, omega R square L square is L by C. So if you substitute R square omega R square plus omega R square plus L square as L by C, we will get YR is equal to RC by L. YR is actually YR is admittance, and impedance is given by 1 by ZR. So ZR is given by reciprocal of this RC by L, L by RC. Okay, this is RC by L, and if you take reciprocal, okay, then ZR is equal to L by RC. It is called as dynamic impedance or dynamic resistance of the practical resonance circuit. Sometimes they will ask you what is dynamic resistance. So at resonance, circuit behaves as purely resistance. Okay, this is why actually admittance. If you take the reciprocal, you will get impedance. So this is called as dynamic impedance or dynamic resistance of a practical, and its formula is given by ZR is equal to L by RC. How it is means, in this part, if you make 0, the circuit behaves as purely this much. But R square plus omega square L square is equal to L by C. This you put L by C, and you'll get expression for Y. Y is equal to RC by L. But ZR is 1 by Y. Okay, ZR is 1 by Y is equal to L by RC. So that is called as dynamic resistance. And current at resonance is given by I is equal to E into R. Okay, I is equal to E into R. Actually, E is equal to I into Z. Okay, Z is nothing but 1 over Y. So I is equal to E into Y. I is equal to E into Y. We know that Ohm's law is V is equal to I into R. Here it is impedance. Z is nothing but 1 by Y. So if we cross multiply, I is equal to E into Y. So at resonance, IR is equal to E into, and YR is given by, RC by L. Or we can also write I is equal to E by Z, no? E by Z, that is V by R, and Z is given by L by RC. It is E into RC by L. So this is the current at resonance. So very very important. You have to derive only up to here. This is additional part. This is additional part. So for the derivation, you have to stop at this point.